So this video should help you with the torque assignment part 2. I just want to go through some of the diagrams that you will see. And unfortunately, we have this problem with the use of the symbols L and D being interchanged. I've taken a lot of these questions from various textbooks, and it seems every textbook uses a different symbol. And I've just kind of winged it for my solution. So I just want to make it clear. The whatever you call it, doesn't matter what the symbol is, but it's the lever arm, which is the perpendicular distance. And you've seen this before, but we'll have to just write it again. Perpendicular distance from axis of rotation to line of action of force. And whether that's called D or that's called L, well, it doesn't really matter. You simply need this distance. Okay, so this first question, I think you've seen this diagram before, and you were told the force on either the feet or the hands and asked for the other one by simply using equilibrium of forces. So in this case, you're not told either the feet or the hands. So there's the force from the feet. There's the force from the hands. And then there's the force of gravity. Now, you're told the force of gravity because you've got the weight of the person, and you're told these two distances, L1 and L2. Now, in this case, notice how everything's nice and perpendicular. So this is the lever arm. Okay, it is perpendicular to the line of action of the force. Now, you've got two unknowns. You don't know the hands force and you don't know the feet force, but you have two equations. And so the two equations, in fact, you can make a whole bunch of equations here. When you define the axis of rotation, you can put it anywhere you want. And you could just write the torque equation out multiple times to find these two unknowns. So two equations are needed when you have two unknowns. This is in general, the number of unknowns, that's how many equations you need. You need when you have two unknowns. And I want to use both translational equilibrium and torque equilibrium. So for torques, remember, clockwise equals counterclockwise. So put the axis of rotation here, because you're used to it on the left. And then do torques. The force of gravity would be a clockwise torque. Lever arm times force is torque. And then lever arm times force, this would be a counterclockwise torque. And beware that the lever arm from the axis of rotation out to the feet is L1 plus L2. Okay, so write out that equation for torques, and you'll be able to calculate the force on the feet. And then you can use forces up equals down. Because once you have the force on the feet, then you know the force on the hands plus the force on the feet must equal the force of gravity. And that would be your second equation. Okay, so this would be equation number 1. Write that out. This would be equation number 2. And you can solve for those two unknowns. Okay, the next one is the biceps, and we have seen this a number of times. The difference here is we're going to calculate this joint force as well. Now, if your hand were to move, I mean, the hand isn't moving right now, but if it were to move up like this, and your joint is the axis of rotation here, well, this upper arm bone would have to push down on your lower arm bone in order for your whole forearm not to lift or drop. Okay, so remember, you put your axis of rotation on the joint. Now, all these L's, these are the lever arms, because notice how everything's nice and perpendicular. So these are the lever arms. Remember, you have to go from the axis to the force, axis to the force, axis to the force. This would be a clockwise torque. This would be a clockwise torque. But this, the tension in the bicep muscle, that would be a counterclockwise torque. And so you just write out clockwise equals counterclockwise for torques. And then you, in order to get the joint force, so to get joint force, so torques to get bicep force, and then to get joint force, use up equals down. So notice how you've got the joint force is down, the weight of the forearm is down, the weight of whatever's in the hand is down, and the bicep muscle is up. Okay, and then that's how you get the joint force for that one. Okay, we've seen that one a couple of times now. Now this is a trickier one. It's really hard to see what's going on in this diagram. So it's a tricep exercise. So as you push down, you push this handle down. Well, the handle exerts a force up like this. So this would be the force from the handle. Let's see, what's the question say? Yeah, so we want the tricep muscle, and it tells you the weight of this mass. So this is the FG of the mass, and the force on your arm is up. So this is the force of the mass is up on your hand. Now, in order to counteract that upward, so that would just make your forearm just fly up, but then your tricep muscle here, which is also up. And you see how close this is? This little distance here, that's the distance between where your tricep muscle pulls up. Remember, muscles can only pull. So this is the tricep muscle. And because your forearm is not horizontal, these two things are not equal to the lever arms. These are the distances along your segment. So these L1, L2, and L3 are the hypotenuse. Hypotenuses of the triangles used to get the lever arms. Okay, so L1, L2, and L3 are not lever arms because your arm is not horizontal. Okay, so how do we get those? So it's kind of tricky. I'm going to kind of blow this up over this little area right here. So your tricep muscle pulls straight up like this. There's your tricep muscle. Your arm is up like this. And we'll make this a big exaggeration here. So from there to there is that little L distance. That's along your arm. This is your elbow. Oh, sorry, that's not your elbow. You can't have your tricep muscle right at your elbow because it would have no lever arm. So I'm going to put the elbows up here. There's your elbow. Okay, that's the axis of rotation. Your tricep muscle is over here to the right of your elbow. And the distance along your body from where your tricep attaches to your elbow, that's the L they're giving you. So that's L, that's the hypotenuse. That's L1. But the lever arm, remember, is the perpendicular distance here. So this is the lever arm for your tricep muscle. And this is theta. Oh man, I meant to make that way bigger. I didn't do a very good job of that. So here's the triangle. That's 90. This is lever arm. And this is distance along your body. And it's this angle that is theta. Okay, so it's the angle between the horizontal and the angle. See how over here, it's a really funny place they've put it, but look what it is. It's the angle between the horizontal and the angle of your arm. So that's this one, because this is your angle of your arm along here. Okay, so this lever arm is cos. You use cos. So lever arm equals L1 cos theta. Okay, so that's how you get that lever arm for that. And then it's the same for these ones. So, except now we're going to go like this. Go across here. There's the lever arm for this force to go straight down like this, which is the weight of your arm. And so this is theta. And again, it's cos. And so it's L2 cos theta to get the lever arm for that one. And then similarly for this one over here, it's cos. They're all cos. Okay, so you use cos for all of these ones to get lever arms. Okay, that's a little tricky one. Okay, for this one, which do we use, sine or cos? So remember, the lever arm is from the axis of rotation, the fulcrum there, that's your elbow. Let me draw that bigger. So here's your elbow. The force is like this. Now we have to go, and then in this case, this one is theta. Now to get from the axis of rotation to the line of action of the force, we go, so we hit it perpendicular, it's like that. This is the lever arm. The hypotenuse is B. Okay, now the question is which angle is which? Well, if that's theta there, then this guy in here is 90 minus theta. This one's theta. And once again, it's cos. So that lever arm would be B cos theta. Okay, the other lever arm for this hanging weight here, this is just A plus B. So you have to add those two together to get the lever arm because it's already perpendicular distance. So that would be here, A plus B. Okay, so that's that one. Okay, this one is not in equilibrium. Okay, it wants you to calculate the torques from these forces acting on the lower leg, the bicep tendon, or sorry, quadricep tendon here, this one, and then the weight of your leg, and then the whatever's on the weight of your foot. Okay, so let's do lever arms here. So axis of rotation is your knee, there's O. And lines of action of these forces are here. And the lever arms for the weight of your leg goes this way, perpendicular. And then this one goes this way out to here, perpendicular. Okay, so now the question is it cos or sine? So let's draw those. We've got the lower leg here. And then we've got the distance along, it'll tell you the distance along the leg. Not sure what they use. I'll call it D for distance along the leg. Okay, this is the knee, that's O. This is the weight. And then I go up here. Oh, I put that in the wrong place. Rats. Well, it doesn't matter. It's this distance from here to here. Doesn't matter whether I draw it there or I draw it up here, doesn't matter. It's this perpendicular distance between axis of rotation and line of action of the force. This is the force of the leg. Okay, so which is which? Well, if this is theta, and this is the lever arm, well, in this case, this side is opposite theta. And so this lever arm, this would be equal to D sine theta. Okay, so that's opposite the angle theta. And it would be the same for this guy. The lever arm would equal distance along your whole leg all the way to your foot, and still sine theta. D foot. Okay, now what about that tendon? What's going on up here? Okay, then we have to draw that a little bigger here. Do I have room? Okay, so for that quadricep tendon, we have the knee. There's the knee, that's O. And then you got your leg, and then you got this tendon here. So this is the quadricep tendon. Force F. Okay, now the angle that you have, phi, is this one, phi. And the perpendicular, remember this is a line of action of the force. I go from O straight over perpendicular. And so this little guy here is the lever arm. That's what you need to calculate the torque. And in this case, if the distance from your knee to where that tendon connects to your shin bone, call that D, that lever arm is opposite the angle phi. So this would be D sine phi. So the quadricep tendon force times D sine phi would be the torque. That would be a counterclockwise torque. So counterclockwise, it would be the T times D sine phi. And this D is from your knee to tendon attachment. Okay, so that's how you do that one. And you'll find out that when you do the torques, now these two guys here are clockwise torques, and the quadricep tendon is a counterclockwise torques, they will not balance. Okay, this is not in equilibrium. The question is, I think they give you all the numbers, and then you have to calculate the torques, and you'll see that the one or the other, I can't remember which, is bigger. So obviously your leg is either going to, your foot's either going to fall down or your foot's going to lift up, depending on which torque is bigger. Okay, similarly, this is not in equilibrium either because we just have one force here. So this is now your hamstring. So obviously you're trying to move your foot like this, like one of those hamstring machines where you're pulling your heels toward your butt. Axis of rotation is here at your knee. So that's O. And it tells you the angle here. So just want to make sure I get the angle. Yeah, it's not the, this is a triangle as well. So D, this is D, but that's not the perpendicular distance of the force because, well, just because it's not. So that's D, this is D. And that's the distance, that's the 6 centimeters. So D equals distance from knee to attachment of that hamstring. But because your leg's at an angle like that, the triangle would look like this. Knee over to your hamstring. So this is O, this is your knee. And then way down here, your hamstring goes like that. That's the force of your hamstring. And that distance along here is D. And so what we need to do, we need to drop, there's a line of action of the force. We need to go down perpendicular. And now which angle is which? When I go like this is 75, which means this must be 75. And this is the lever arm, the perpendicular distance. And that lever arm is opposite the 75. And so this lever arm would equal D sine 75. And the D is the 0.06 meters. Okay, so that would be L, I guess, for lever arm. Okay. It's not trivial, these diagrams. You have to sort of see them. And on a test, I will give you like similar diagrams. I'll just change the numbers. Okay, so here's one. Again, we have some different angles here. So this is your hips. That's your hips. And this bar is your back. That's here. Okay. And it is at 30 degrees. Here, this is 30 degrees. So you're leaning over, so that's 30 degrees. Now, the force of gravity from your head and arms is there. Force of gravity from your torso is here. So this is head, this is torso. And those two things are going to exert clockwise torques. And their lever arms are these distances. We've seen this quite a few times, this one. It's like this. And then this lever arm would be over here. And it's close to 30. So this one would be the full. Now, notice how they don't tell you how long your torso is, but they tell you that the center of mass is halfway up, half L, and that the end, now what's the 2/3? Oh, 2/3 L is where the attachment of this erector spinae muscles are. And then obviously L is the full length. Now, L, it's going to cancel out everywhere, but if it bothers you, just let L be something. Let L be, let's see, how far do you think it is from your head to your hips? Maybe a meter. Just let L equal 1 meter, and then you can just calculate all the distances. Now, that's not the lever arm. This is the length of your torso from your hips to your head. Okay, so, but the lever arms are the distance along your back times cosine 30. So, okay, I'll do it like this. So lever arms are equal to distance along back times cosine of 30 degrees. Okay, and you're going to have to do that for the torso and for the head. Now, for the erector spinae muscle, it's totally different because it's a different angle. So we'll do the muscle. Okay, so this lever arm for head and torso, oopsie, torso forces of gravity. But the lever arm for that erector spinae muscle, so there's the force from the muscle. Oops. This is 12 degrees. There's the axis of rotation O. And so we have to go hit this perpendicular. Perpendicular. This is the distance along your back. This would be the 2/3. Is it 2/3 of L? Yeah, 2/3 of, no. Yep, 2/3 of L. That's always the, remember the distance along your body is always the hypotenuse. This is the lever arm for that muscle. And because it's opposite 12 degrees, the lever arm here would be the 2/3 L times sine of 12 degrees. And this is for erector spinae muscles. Oops, spelled that wrong. It's I-N-A-E muscles. Okay, and remember you're doing, now this is in equilibrium. And so you're trying to calculate the tension in this muscle here, this erector spinae muscle, because it's at such a small angle relative to your back. This lever arm is really small, and it's really difficult for that muscle to exert a torque to hold up your torso. So this is going to be a huge force. This will be huge compared to the weight of your head and torso itself. So this is why, and it's got a huge compressional component, right, that runs along. So here's your back, And this being 12 degrees is itty bitty. It's just like this. And so remember, it's got this compressional component, and it's got look at the rotational component. That's tiny. So that it's the rotational component that produces the torque that holds your back up. And so just imagine how big this force in the muscle has to be so that that rotational component exerts enough torque to counteract the weight of your body and your head. And this compressional component is the one that simply squishes your vertebra together. And that causes all kinds of problems. So once you have the force along the muscle, so this is the force along muscle, using torques, you just found that. Now you can get the rotational component. That would be F sine 12. And then the compressional component would be F cos 12. And I think that's what they ask you in the part B. Now, I don't think this question asks, but you could also work out the force at the hips, right? Now, you've got all these, you've got the weight of your body. Obviously, this thing, your hips have to support your back, or your whole back would just fall to the ground. And so there is an upward force, but it also has to counteract this compressional component of the rectus spinae muscles. And so your hip also has to exert a force up your back, and then those two squish your spine together. Okay, so I think the next couple are very simple diagrams, and you should be able to figure them out on your own. So that'll be it for now.